Moore's law is the observation that the number of transistors in a dense integrated circuit doubles approximately every 2 years. The observation is named after Gordon E. Moore, the co-founder of Intel and Fairchild Semiconductor, whose 1965 paper described a doubling every year in the number of components per integrated circuit, and projected this rate of growth would continue for at least another decade. In 1975, looking forward to the next decade, he revised the forecast to doubling every 2 years. His prediction proved accurate for several decades, and the law was used in the semiconductor industry to guide long-term planning and to set targets for research and development. Advancements in digital electronics are strongly linked to Moore's law. Quality-adjusted microprocessor prices, memory capacity, sensors, and even the number and size of pixels in digital cameras. Digital electronics have contributed to world economic growth in the late 20th and early 21st centuries. Moore's law describes a driving force of technological and social change, productivity, and economic growth. The period is often quoted as 18 months because of Intel executive David House, who predicted that chip performance would double every 18 months. Moore's law should be considered an observation or projection and obviously not a physical or natural law. Although the rate held steady from 1975 until around 2012, the rate was faster during the first decade. In general, it is not logically sound to extrapolate from the historical growth rate into the indefinite future. For example, the 2010 update to the International Technology Roadmap for Semiconductors predicted that growth would slow around 2013, and Gordon Moore in 2015 foresaw that the rate of progress would reach saturation. I see Moore's law dying here in the next decade or so. Intel confirmed in 2015 that the pace of advancement has slowed, starting at the 22 nanometers feature width around 2012, and continuing at 14 nanometers. Brian Krzanich, CEO of Intel, announced that our cadence today is closer to 2.5 years than 2. This is scheduled to hold through the 10 nanometers width in late 2017. He cited Moore's 1975 revision as a precedent for the current deceleration, which results from technical challenges and is a natural part of the history of Moore's law. History. In 1959, Douglas Engelbart discussed the projected downscaling of integrated circuit size in the article, Microelectronics and the Art of Similitude. Engelbart presented his ideas at the 1960 International Solid-State Circuits Conference, where Moore was present in the audience. For the 35th anniversary issue of Electronics magazine, which was published on April 19, 1965, Gordon E. Moore, who was working as the Director of Research and Development at Fairchild Semiconductor at the time, was asked to predict what was going to happen in the semiconductor components industry over the next 10 years. His response was a brief article entitled, "Cramming More Components onto Integrated Circuits." The complexity for minimum component costs has increased at a rate of roughly a factor of 2 per year. Certainly over the short term this rate can be expected to continue, if not to increase. Over the longer term, the rate of increase is a bit more uncertain, although there is no reason to believe it will not remain nearly constant for at least 10 years. His reasoning was a log-linear relationship between device complexity and time. At the 1975 IEEE International Electron Devices meeting, Moore revised the forecast rate. Semiconductor complexity would continue to double annually until about 1980, after which it would decrease to a rate of doubling approximately every 2 years. He outlined several contributing factors for this exponential behavior. Die sizes were increasing at an exponential rate, and as defective densities decreased, chip manufacturers could work with larger areas without losing reduction yields. Simultaneous evolution to finer minimum dimensions, and what Moore called circuit and device cleverness. Shortly after 1975, Caltech professor Carver Mead popularized the term Moore's law. Despite her popular misconception, Moore is adamant that he did not predict a doubling every 18 months. Rather, David House, an Intel colleague, had factored in the increasing performance of transistors to conclude that integrated circuits would double in performance every 18 months. In April 2005, Intel offered $10,000 to purchase a copy of the original electronics issue in which Moore's article appeared. An engineer living in the United Kingdom was the first to find a copy and offer it to Intel, as a target for industry in a self-fulfilling prophecy. Although Moore's law initially was made in the form of an observation and forecast, the more widely it became accepted, the more it served as a goal for an entire industry. This drove both marketing and engineering departments of semiconductor manufacturers to focus enormous energy aiming for the specified increase in processing power that it was presumed one or more of their competitors would soon attain. In this regard, it may be viewed as a self-fulfilling prophecy. Moore's second law: as the cost of computer power to the consumer falls, the cost for producers to fulfill Moore's law follows an opposite trend. R&D, manufacturing, and test costs have increased steadily with each new generation of chips. Rising manufacturing costs are an important consideration for the sustaining of Moore's law. This had led to the formulation of Moore's second law, also called Rock's law, which is that the capital cost of a semiconductor fab also increases exponentially over time, enabling factors and future trends. Numerous innovations by scientists and engineers have sustained Moore's law since the beginning of the integrated circuit era. A few innovations are listed below as examples of breakthroughs that have advanced integrated circuit technology by more than 7 orders of magnitude in less than 5 decades. The foremost contribution, which is the raison d'être for Moore's law, is the invention of the integrated circuit. Credited contemporaneously to Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor. The invention of the complementary metal oxide semiconductor process by Frank von Lass in 1963, and a number of advances in CMOS technology by many workers in the semiconductor field since the work of von Lass have enabled the extremely dense and high-performance ICs that the industry makes today. The invention of the dynamic random access memory technology by Robert Dennard at IBM in 1967 made it possible to fabricate single-transistor memory cells, and the invention of flash memory by Fujio Masuoka at Toshiba in the 1980s, leading to low-cost, high-capacity memory in diverse electronic products. The invention of chemically amplified photoresist by C. Grant Wilson, Hiroshi Ito and J.M.J. Frechet at IBM c. 1980, that was 10 to 100 times more sensitive to ultraviolet light. IBM introduced chemically amplified photoresist for DRAM production in the mid-1980s. The invention of deep UV excimer laser photolithography by Kanti Jine at IBM c. 1980 has enabled the smallest features in ICs to shrink from 800 nanometers in 1990 to as low as 22 nanometers in 2012. This built on the invention of the excimer laser in 1970 by Nikolai Basov, A. Danilychev and U. M. Popov at the Lebedev Physical Institute. From a broader scientific perspective, the invention of excimer laser lithography has been highlighted as one of the major milestones in the 50-year history of the laser. The interconnect innovations of the late 1990s include that IBM developed CMP, or chemical mechanical planarization c. 1980. Based on the centuries-old polishing process for making telescope lenses. CMP smooths the chip surface. Intel used chemical mechanical polishing to enable additional layers of metal wires in 1990, higher transistor density via trench isolation, local polysilicon, and improved wafer yield. Higher yield, the fraction of working chips on a wafer, reduces manufacturing cost. IBM, with assistance from Motorola, used CMP for lower electrical resistance copper interconnect instead of aluminum in 1997. Computer industry technology roadmaps predict that Moore's law will continue for several generations of semiconductor chips. Depending on the doubling time used in the calculations, this could mean up to a 100-fold increase in transistor count per chip within a decade. The semiconductor industry technology roadmap uses a 3-year doubling time for microprocessors, leading to a 10-fold increase in the next decade. Intel was reported in 2005 as stating that the downsizing of silicon chips with good economics can continue during the next decade, and in 2008 as predicting the trend through 2029. Some of the new directions in research that may allow Moore's law to continue are: in 2008, researchers at HP Labs announced a working memristor, a fourth basic passive circuit element whose existence only had been theorized previously. The memristor's unique properties permit the creation of smaller and better-performing electronic devices. In 2010, researchers at the Tyndall National Institute in Cork, Ireland announced a junctionless transistor. A control gauge wrapped around a silicon nanowire can control the passage of electrons without the use of junctions or doping. They claim these may be produced at 10 nanometer scale using existing fabrication techniques. In 2011, researchers at the University of Pittsburgh announced the development of a single electron transistor, 1.5 nanometers in diameter, made out of oxide-based materials. 3 wires converge on a central island that can house 1 or 2 electrons. Electrons tunnel from one wire to another through the island. Conditions on the third wire result in distinct conductive properties, including the ability of the transistor to act as a solid-state memory. Nanowire transistors could spur the creation of microscopic computers. In 2012, a research team at the University of New South Wales announced the development of the first working transistor consisting of a single atom placed precisely in a silicon crystal. Moore's law predicted this milestone to be reached for ICs in the lab by 2020. In 2014, bioengineers at Stanford University developed a circuit modeled on the human brain. 16 neurocore chips simulate 1 million neurons and billions of synaptic connections, claimed to be 9,000 times faster as well as more energy efficient than a typical PC. In 2015, IBM demonstrated 7 nanometers node chips with silicon germanium transistors produced using EUVL. The company believes this transistor density would be 4 times that of current 14 nanometers chips. In 2015, Intel and Micron announced 3DX Point, a non-volatile memory claimed to be up to 1,000 times faster, up to 1,000 times higher endurance and similar in density compared to NAND. Production is scheduled in 2016. Speculation on limits. On April 13, 2005, Gordon Moore stated in an interview that the projection cannot be sustained indefinitely. It can't continue forever. The nature of exponentials is that you push them out and eventually disaster happens. He also noted that transistors eventually would reach the limits of miniaturization at atomic levels. In terms of size of transistors, you can see that we're approaching the size of atoms, which is a fundamental barrier. But it'll be 2 or 3 generations before we get that far, but that's as far out as we've ever been able to see. We have another 10 to 20 years before we reach a fundamental limit. By then they'll be able to make bigger chips and have transistor budgets in the billions. Some see the limits of the law as being in the distant future. Lawrence Krauss and Glenn D. Starkman announced an ultimate limit of approximately 600 years in a paper, based on rigorous estimation of total information processing capacity of any system in the universe, which is limited by the Bekenstein bound. On the other hand, based on quantum theory and the laws of thermodynamics, there are predictions that Moore's law will collapse in the next few decades, 20 to 40 years. Then again, the law often has met obstacles that first appeared insurmountable, but were indeed surmounted before long. In that sense, Moore says he now sees his law as more beautiful than he had realized. Moore's law is a violation of Murphy's law. Everything gets better and better, consequences and limitations. Technological change is a combination of more and of better technology. A 2011 study in the journal Science showed that the peak of the rate of change of the world's capacity to compute information was in the year 1998. When the world's technological capacity to compute information on general-purpose computers grew at 88% per year. Since then, technological change clearly has slowed. In recent times, every new year allowed humans to carry out roughly 60% of the computations that possibly could have been executed by all existing general-purpose computers before that year. This still is exponential, but shows the varying nature of technological change. The primary driving force of economic growth is the growth of productivity, and Moore's law factors into productivity. Moore expected that the rate of technological progress is going to be controlled from financial realities. The reverse could and did occur around the late 1990s. However, with economists reporting that productivity growth is the key economic indicator of innovation, an acceleration in the rate of semiconductor progress contributed to a surge in U.S. productivity growth, which reached 3.4% per year in 1997 to 2004, outpacing the 1.6% per year during both 1972 to 1996 and 2005 to 2013. As economist Richard G. Anderson notes, numerous studies have traced the cause of the productivity acceleration to technological innovations in the production of semiconductors that sharply reduce the prices of such components and of the products that contain them, while physical limits to transistor scaling such as source-to-drain leakage, limited gate metals, and limited options for channel material have been reached. New avenues for continued scaling are open. The most promising of these approaches rely on using the spin state of electron spintronics, tunnel junctions, and advanced confinement of channel materials via nanowire geometry. A comprehensive list of available device choices shows that a wide range of device options is open for continuing Moore's law into the next few decades. Spin-based logic and memory options are being developed actively in industrial labs, as well as academic labs. Another source of improved performance is in microarchitecture techniques exploiting the growth of available transistor count. Out-of-order execution and on-chip caching and prefetching reduce the memory latency bottleneck at the expense of using more transistors and increasing the processor complexity. These increases are described empirically by Pollak's rule, which states that performance increases due to microarchitecture techniques are square root of the number of transistors or the area of a processor. For years, processor makers delivered increases in clock rates and instruction-level parallelism, so that single-threaded code executed faster on newer processors with no modification. Now, to manage CPU power dissipation, processor makers favor multi-core chip designs, and software has to be written in a multi-threaded manner to take full advantage of the hardware. Many multi-threaded development paradigms introduce overhead, and will not see a linear increase in speed versus number of processors. This is particularly true while accessing shared or dependent resources, due to lock contention. This effect becomes more noticeable as the number of processors increases. There are cases where a roughly 45% increase in process of transistors has translated to roughly 10 to 20% increase in processing power. On the other hand, processor manufacturers are taking advantage of the extra space that the transistor shrinkage provides to add specialized processing units to deal with features such as graphics, video, and cryptography. For one example, Intel's parallel JavaScript extension not only adds support for multiple cores, but also for the other non-general processing features of their chips, as part of the migration in client-side scripting toward HTML5. A negative implication of Moore's law is obsolescence, that is, as technologies continue to rapidly improve, these improvements may be significant enough to render predecessor technologies obsolete rapidly. In situations in which security and survivability of hardware or data are paramount, or in which resources are limited, rapid obsolescence may pose obstacles to smooth or continued operations. Because of the toxic materials used in the production of modern computers, obsolescence, if not properly managed, may lead to harmful environmental impacts. On the other hand, obsolescence may sometimes be desirable to a company which can profit immensely from the regular purchase of what is often expensive new equipment, instead of retaining one device for a longer period of time. Those in the industry are well aware of this, and may utilize planned obsolescence as a method of increasing profits. Moore's law has affected the performance of other technologies significantly. Michael S. Malone wrote of a Moore's war following the apparent successive shock and awe in the early days of the Iraq War. Progress in the development of guided weapons depends on electronic technology. Improvements in circuit density and low-power operation associated with Moore's law also have contributed to the development of technologies including mobile telephones and 3D printing.